About the flow called let me see, pulsating. Okay, I think we finished. We have this problem before. Okay, pulsating flow. Okay, so pulsating flow. Okay, we have between two parallel plates, so that we have the unsteady pressure source, right? So partial P partial A is the cosine function, cosine NT, T is our time. Okay, so this is unsteady pressure wave. Okay, we have unsteady pressure to driven our flow with between two parallel plates. Okay, so this is the carbon equation. Okay, in the X momentum equation, and then by using the previous, okay, we try to do is we try to using so-called separation of variable. Okay, and separation of variable U is function of Y and T, right? So here is a kind of a flow with two parallel plates, okay, and our coordinate system is X and Y. So U velocity is like this, okay, but this U is unstable, sometimes like that. So we change, okay, according to your pressure weight. So your pressure weight dx is dx cosine nt. Okay, so this is time, change with time. So our pressure, our flow U velocity is function of Y and T. Okay, we try to solve this problem. Okay, we have unstable pressure wave driven unstable here, driven the flow back and forth. Okay, so that's the physical problem. Okay, we have. So this is very similar to the some of the biomechanics. Okay, inside your blood vessel. Okay. 在你的血液里面，心脏就是一个 pulsating 的一个 unsteady. In our heart, our pressure is unsteady, right? Inside our circulation system, our body, okay? And we'd like to know how the flow inside the tube, okay? And what happened, the flow pattern look like, and that will be applied to the biomechanics, biofluid mechanics a lot. So here is since our flow is U velocity is a function of Y and T. Okay, so is a function of Y and T. So we're using the separation of variable. Since our time domain is a sine cosine function, so we assume our velocity also sine cosine function. So its potential INT represent the cosine NT plus I sine NT. Okay, so that will be composed by since from this unsteady cosine NT, and our Y direction we're using the function WY. So our variable U is a function of YT, but we're using so-called separation of variable. In separation of variable, W is only function of Y, and this is potential INT is only function of time. So these two variables, Y and T, is separate into two functions. Okay, and we can in the partial differential equation we can solve that by using this method called separation of variable. And we take a real part of this because this is cosine nt, so this is the cosine. Okay, so we substitute this solution form into this action momentum equation, and you get this. Okay, and eventually you will get the W function, and you can solve the W function. Since W is only function of Y, so eventually you will get one so-called ODE, Oden differential equation of the W. Okay, this is Oden differential equation for the W. Okay, so this is d squared W dy squared. This is second order term. We don't have any first order term, but we have a W term here. And this is our what? Non-homogeneous term. Okay, so we can solve this non-homogeneous what? ODE. Okay, so one of our homework in this week, okay, I think already the deadline is on Thursday. Okay, it's actually to do is by using this, okay, with this boundary condition, and try to solve this, okay, by yourself. Try to go back to your engineering analysis book or engineering mathematics book. Okay, you should be able to find a solution. Look like this. Okay, since we jumped a little bit from here, so I would like you to make it up. Okay, try to derive from this solution and get this. So here is about W function. Okay, W function. Okay, So W function is function only the y only, right? A is our boundary condition because y positive negative A is equal to 0. This is y equal to positive A, this is y equal to negative A, okay? Our x location is here. Okay? So that's the boundary condition for the non-C boundary condition. Okay, so the U should be equal to 0 on the wall. Y equal positive and negative A, that's on the wall, okay? Our U velocity should be equal to 0. That's the non-state boundary condition. Okay, so that will be the solution for the W here. So W solution times its potential INT to take a real part, give you the, okay, give you the solution. So here is the solution. U is the real part of what? Real part of WY is this. Okay, is all everything here. Okay, times its potential INT, times its potential INT here. So the rest of here is just our WY. Okay, so that's a solution form. Okay, complete solution form. Okay, and I think if you want to expand this, it will be a horrified mess. Okay, that's a horrible mess. That means it's become too complicated. Okay. So we just stop here. However, we can have a little discussion about this solution form. Okay, and discussion of this solution form, okay, will be based on two discussions. One discussion called the Lorentz number, okay, and if you see this term here, square root of n over 2 mu a here, okay. If you move this a into this square root, become a square n over 2 mu. A square n over 2 mu here can be defined as R sub n. And R sub n, it can be equivalent to so-called Reynolds number. Okay? And I already mentioned that. Okay. A is a length scale, right? N is what? N is frequency. Okay? So if you do the dimensional analysis, A square n over 2 mu, A square n over 2 mu here. That's our Reynolds number definition. Why this is Reynolds number? As you can see, Reynolds number definition is log mu L divided by mu, right? Or UL divided by mu, right? And we already mu is here. So on the denominator, on the UL here can be equivalent to A is the length scale, right? And n is 1 over t, right? N is 1 over t. So this is length scale over 1 over t. So the dimension for this, we can divide it from A times an, and A is our length scale, okay? And then A is a length scale. N is what? N is a frequency, is 1 over t. So this becomes U here. And this becomes L. So this is equivalent to Reynolds number definition. Okay? So that will be we can discuss this. Okay? This is we define as a Reynolds number. Okay, and you should notice why this is Reynolds number. And when Reynolds number much less than 1, what happened? Okay, what's the physical meaning of much less than 1? Okay, physical meaning for this is okay, our flow is either very slow motion, okay, or our viscosity is big. Okay, there are two possibilities. One is the flow is very slow, moving very slowly. Okay, that represents the Lorentz number, right? Another possibility, you change your fluid, what? To very viscous fluid. Okay, and very viscous fluid, our mu is huge, right? So this becomes smaller. So you can make this, okay, Reynolds number smaller by using these two possibilities. Okay, so as you can see, we have hypercosine function here. This is another hypercosine function as of y here. Okay, so and hypercosine function you can use in the so-called Taylor expansion. You can find in your mathematics book. This is Taylor expansion for hypercosine function. Okay, and if this x is a small value, as you can see, if this is a long Reynolds number, that means this is very small value. And this small value, as you can see, 1 plus x squared over 2 factor plus x to the 4th order and divide over 4 factor, right? Factor 4. As you can see, when x becomes smaller, x squared even smaller. x force, the force over even smaller. Okay, so we can keep only the leading edge, leading term. Okay, that means the 1 plus this term, and the rest of term can be cancelled or can be neglected. Okay, so as you can see, on the cosine, this function here become 1 plus 1/2 because factor of 2 is equal to 1/2. So 1/2, okay, and times what? Times this function, right? This function. So this is a function we have, and this function, as you can see, is a square root, and this function square. I'm sorry, this x square, right? X square is this square. So 1 plus I square become 2I here, okay, and then this square become n over 2 mu because it is a square root, but after the square become n over 2 mu, and the y become y square. Okay, so this is x square become like this, and we also on the denominator here we do the similar thing. 1 plus 1/2 of x square. X square, this is x, so this is x square. Okay, and then you can also apply so-called approximation solution. Okay, again here do the 1 plus a small value. Okay. Let's apply this. 1 plus a small value, okay, is equal to 1 minus small value. Okay, so this is each known is very small number. Okay, so we have this kind of approximation. Okay, so on the denominator here, 在分母这个地方 okay, 1 plus a small number because our Reynolds number is smaller, right? This is n square, na square over 2 mu is a very small number. So here 1 plus a small number over, okay, in the denominator become 1 minus of this, right? The 1 minus of this, okay? And this 2 and 2 is cancel, only I, okay, here. So while the sign is a positive sign here, become negative sign here, you should be able, okay? Let's apply this form here. Okay, again, this will be multiplied by this, right? A sequence of the number, a sequence of this series, okay? Multiply a series. And again, this is very small number, right? And then so we can also take a very leading order term. What's the leading order term? 1 multiplied by 1 equal to 1. And then this term here, right? This term multiplied by 1. And also this term multiplied by 1. Is all, okay, leading order term. And then when you have encountered this term multiplied by this term, it's even smaller. Okay, we just neglect it because this term is very small and this term is even smaller. So we can second order term. So we neglect all the second order term. Only keep the leading first order term here. So if you do that, you can approximate equal to 1 plus I r n and y over a square. So that's a solution, okay, for this approximation form for this function here. Hypercosine function over this hypercosine function will be close to this. Okay, will be very, very close to this. Okay, so we plug this solution form into here and try to find out uy. As you can see, this is u function of yt, and then is equal to real part of this term here, and 1 minus this term, 1 minus this term here, under this kind of Reynolds number condition. So this we have 1 here, and this is 1 minus this, and this 1 is cancelled, right? And we only have this term here, okay, for this, okay, for this. So we end up with this, okay, end up with this, okay. Okay, so we kind of we take this is a real part of this. The cosine, this is exponential int is what? Exponential int is a cosine int plus I sine nt, right? And then this is minus I here, right? And this I and I is equal to, I minus I is equal to minus 1, and this minus sign is cancelled, right? So for this term here, we take a real part, become cosine nt, and rest of part is a real part, okay? It's only real number, so this is real number. Okay, so this is under the so-called long-range number, okay, condition. Our solution can reduce to this, can reduce to this. Okay, and if you compare, okay, from the previous, we already studied steady state velocity profile within the pipe flow. Okay, as you can, this is a copy from the previous lecture. Okay, you can check. If I have a pipe flow with a pressure gradient, this pressure gradient is constant, and then I got this solution. Okay, this is our velocity profile with a steady state velocity profile. Okay, if you compare these two, as you can see here, this term and this term is almost the same, right? And this is if I take a squared out of here, okay, and it's 1 minus r squared over. So this is similar like here. So everything is very similar. Okay. So even as you can see here, this physical problem is unsteady piping flow, right? Pulsating pipe. So pulsating pipe is unsteady. We have an unsteady turn here. Okay. And our velocity profile, okay, as you can see here, even is a function of time. And then our solution form is compared with our steady state solution form is almost the same. Okay, that's what's the physical meaning. Physical meaning is what? Since under the Lorentz number condition here, okay, and our flow, our velocity profile has exact the same form as a constant pressure gradient. Okay, since this is under the constant pressure gradient, and this is unsteady pressure gradient, and they have a very, very similar solution form. Okay, so that means our flow can be regarded as what? As a quasi-steady. Okay, quasi-steady. Okay. You don't have to assume this is unsteady. We can assume at a certain moment the pressure gradient, and give me this pressure gradient, and we regarding this pressure gradient as a constant at that moment, and then try to derive this equation. We get that at that instant our time velocity profile at that time. So we can assume it's so-called a quasi-steady. Okay. So in this case, as you can see, since even our partial p partial x is a function of time, right? Because the partial p partial is what? Partial p partial is the ps cosine nt here, right? It's a function of time. It's changing, right? It's changing. However, our flow velocity, and then with a partial p partial x, the solution form like this, our flow is in phase with our pressure gradient. Okay, when I mean in phase, if this is a cosine function, our velocity is what? It's also cosine function. So that will look like this. If you go back to it, this is not in your lecture note. I just add this for you to understand. If I have a pressure gradient like this, okay, pressure is higher and low, negative and low and higher. They like change with a cosine function. Okay, this is our cosine function. Minus dp dx is minus, so this is our, and if you see the flow field, at this time, okay, pressure is a minus dp dx is a positive, I have a forward flow. And when the pressure is decreased to 0, I have almost no flow. When pressure is negative, I have reverse flow. It's almost in phase with what is our pressure gradient. Okay, that means the red line here represents our velocity profile, okay, at the center point. Okay, when y equal to 0, as you can see, y equal to 0, this term drop, right? Y equal to 0 represent the velocity at this location at different time. Okay, when y equal to 0, and then y equal to 0, we have a measurement mark here, and then compare with the dp dx, they almost synchronize with the phase. Okay, because this is a cosine function, this is a cosine function. Okay, they don't have any difference. Okay, so we have a higher pressure, forward pressure, dp dx is a minus dp dx is the highest measurement mark. We have a measurement mark velocity. Okay, that's a represent for this case. We're in phase with a pressure gradient. Okay. Okay, so that this here we have a comment here is because this is our Lorentz number, our inertial effect are negligible. Okay, that's That's cause our, okay, this velocity and the pressure is in phase. Okay, here we discuss another, okay, case. Another case, we have a hydrogen chamber. That means the R sub n here is much greater than 1. And we also using the solution form like here, right? This is a complete solution form. And when this term here is much greater than 1, that means the hydrogen chamber here. Okay? So hypercosine function like this should be changed, okay, accordingly. And what's the definition of hypercosine function? Is 1/2 of exponential x plus exponential minus x, right? If you remember that, hypercosine function is what? Hypercosine function is like this, right? It's hypercosine z is equal to hypercosine exponential z plus exponential minus z. Okay, that's a definition of hypercosine function. Okay, and we have a hypercosine function here and hypercosine function here. And this argument inside this hypercosine function, when this number is huge, okay, and this is a complex number, so like z here, z is a complex number. And z can be changed to what? R is potential I theta, right? Because using the polar coordinate. Okay, so and this is minus z become minus R EI theta. And then you can extend that, okay? You can extend that because EI theta, exponential I theta is a cosine sine function only. Okay, it's a bounded function within 1, right? And then the R is what? When this absolute value of z is equal to R, when R is much greater than 1, as you can see, this is exponential minus this, and exponential minus this. When this is become bigger, much bigger than 1, this term is exponential decay, right? This term is exponential decay. So this term can be dropped. So hypercosine function when z is much greater than 1, we only have this term here. So the first term, the E is potential z over 2. So we're using this here. So since this is a big number, right? This is much greater than 1, okay? Because of hydrogen number. So here we have a 1/2 of the exponential of this, okay? And on the denominator here, we also have exponential of this over 2, and so this will become exponential of this over exponential of this. Okay, that's because of when you have a hydrogen chamber here. Can you follow me? 可不可以跟得上？就是当你这个很大的时候，对，这个只剩下这一项，后面这一项是 thermal decay， 所以这个就剩下这个。所以 here we have a huge number here, so it becomes exponential, okay, function here. Okay, so we have two exponential function, so become this exponential function over this exponential function will be equal to exponential of this minus this, right? So it can be rearranged like this. So this argument minus this argument can be combined together. Okay. 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 So here is our Reynolds number square, right? Well, this is our Reynolds number, and then this is our Reynolds number 1/2. Okay. I think this is missing of a somewhere. Yeah. No. We take this a out of here, right? And then this will become our Reynolds number 1/2. Okay, square root of Reynolds number here. So here is this function, this hypercosine function, okay, can be simplified, can be approximated by using this exponential function when the hydrogen number assumption. Okay, and as you can see here, okay, this is exponential minus a number, right? A number. And since our Reynolds number is much greater than 1, so this is minus sign, and this is much greater than 1. That means this is exponential minus of huge number. That means exponential decay, right? So this is very small number, but except what? if this is not a very small number, okay, so except in the very thin boundary layer, except in the thin boundary layer, in the thin boundary layer, y is okay, is approximately equal to 1, and this is not this is a very small number, okay, and this big number multiplied by a small number may not be small enough, okay, so that's mean within the boundary layer here we have to take into account, okay, later. Okay, if this is a finite number, this is a big number, and its potential minus a big number, this is its potential decay. There's no problem. However, within the boundary layer, when this term here, okay, within this range, and multiply this and this may not be a big number anymore. Okay, so that's mean within the thin boundary layer, we have to take into account later. Okay, but outside the boundary layer, okay, that will be okay. Okay, so as you can see here, our exponential function, this is our this is function here. And again, we apply this function into what? Into this solution form, right? Because we just evaluate this function under the Heilong number. And then we'll try to find that uy is real part of this times 1 minus this. And so that will give you the 1 minus this, right? And then, so as you can see here, okay, is our uy, okay, will be equal to what? It will be equal to plug into the, okay, and then we try to find out the solution form at what? Near the core region. Near the core region means near the flow here. This is the core region. Okay, this is the core region. We call this the core region. But so near the core region is here, y is not within the same boundary layer. So this term is not, okay, small enough, it's not big enough, okay. So it's not small enough, I'm sorry, this is a big number. So this is its potential decay will be equal to 0, right? So in the core region here, the core region, as you can see here, if I do that, I think I didn't do that here, right? I think I forgot to do that here to make me easier. I plug into this solution form, as you can see here. Okay, so this is u of a function of yt is equal to real part of what? Real part, okay, of itx over rho n, right? It's potential int, and times 1 minus its potential, because the cosine function here, okay. Hypercosine over hypercosine, this function here, okay, can be simplified when you have a Heilong number. This hypercosine function can be represented as this, okay. And I take this because this is a big number, so this is potential minus a big number. This is a huge number, big number, right? Because Heilong number is a big out in the core region. Core region. So this is potential, okay, and we neglect it because it's potential decay in the core region. So here inside here become 1. So our function become what? Our u velocity become itx rho n. Its potential int take the real part of what? It's a cosine. Right? Let me check. Here. I'm sorry, okay. It's potential int, and I have to multiply this I forgot this I here. Okay, so here's I here, right? And I and its potential int, I make a mistake here. Remember, this is real part of this, right? Real part of this. So I have the I, and this is potential int is equal to cosine nt plus I sine nt. Right? And this I and I become minus 1. The minus 1 become take the real part. The real part becomes sine nt here. Okay? Instead of cosine nt. This should be changed to sine nt. Okay? Take the minus sign, but I times I. Okay? So you should check it, okay? When you have this and times this, take a real part, become the sine nt here. Okay,